What's up, everybody? Video number 3 for the week here. Happy, who knows what day it is anymore. But let's jump in. So today we're going to do some math. Just a couple quick problems. We want to look at how can we find margin of error for a t interval, and how can we find sample size given some margin of error and some other information. So we're just going to do 2 examples. Let's just jump in. So here we go. So first up, video 3 here, finding margin of error and sample size. So first question. So we've got some undergraduate, some credit bureau's analysis of undergraduate students' credit cards, and they claim that the average number of credit cards undergrads carry is 4.09. Don't do that. That's like a lot of credit cards. Maybe 1, preferably 0 when you're in college there. Don't get a bunch of credit card debt. Nonetheless, to investigate this claim, we get a random sample of 132 undergrads. There's our N. Amongst those 132, our sample mean, our X bar, we had a sample mean of 2.6 credit cards per undergrad with a standard deviation. There's our SX of 1.2. And our job right now is to calculate the margin of error for our 98% confidence interval. So since we're talking interval's only based on sample data, right? We're using a sample data to draw conclusions about to estimate some population parameter, in this case, using X bar to estimate mu. So since we're just working with sample data, this number is irrelevant. So, right, all the big ideas are the same. We just have to tweak the math. So hopefully we're immediately remembering that the margin of error, right, that's everything after the plus or minus, everything after our statistics. So our margin of error, we just need to do the critical value times the standard error of our statistic. So let's do that. So let's jump over to the whiteboard here. So margin of error, probably would help if I click share for real. Margin of error is critical value, right, times standard error of our stat. Critical value, that's our T star, and in this case, we have 131 degrees of freedom, right, N minus 1. This standard error formula for one sample mean is given on the formula sheet, and that's our SX over the square root of N. So find margin of error, we just got to pop some numbers into a formula, no big deal. Now this part is pretty easy. Sample standard deviation was 1.2 over the square root of 132. But our critical value is going to take some work. Now, we could look it up in the t-table, right? So we could look for 131 degrees of freedom down the left and 98% confidence in the bottom and see where those meet. The paper t-table, if we were in class, the t-table that I would be giving you would not have 131 degrees of freedom on it, right? You could probably Google that, I would imagine, pretty easily, right? 131 degrees of freedom, critical value, whatever, 98% confidence. But if we understand what's going on with this, a faster option, what I'm going to do is I'm going to jump over and think about some of the stuff we used in yesterday's video. So we want to find T star for 131 degrees of freedom and a 98% confidence level. So remember, try to draw some fatter tails here. Remember, we're trying to figure out what t-score now, and this would just be the negative, contains 98% of the data. I don't know why I'm making my 8 so weird. 98% in the middle, right? That leaves 1% here and 1% here. So to get this t star, now on a side note, I would not give a question like this if we were in class because not every calculator has inverse t on it, but whatever. For now, learn stuff. To get this, I'm just going to go inverse t, because if we want to go from a percentage back to a t-score, percentage back to a data value, that's our inverse stuff. My area is going to be 0.01, and my degrees of freedom are 131. Right, so we need the area to the left and then the degrees of freedom, and that's going to come out to be, I believe, negative 2.355. Just ignore the negative sign. You know, if we want, we could use this spot, and if I'm going to find this positive t-score, right, we know it should be positive 2.355. I'm just going to do inverse t, but this time my area is 0.99. Because to the left of this spot, we got the 98% in green plus this 1% over here, and then 131. And just in case you don't believe me, we'll go second vars What's happening? My calculator's freaking out. Why is nothing happening when I press buttons? That seems bad. We're going to go second vars, inverse t. 0.0, we'll go 0.99, 131. Hopefully that wasn't lying. All right, cool, I'm not lying. So then we jump back over to here. And so now we know this was 2.355. So this is how I calculate margin of error. So I got a couple options. I can do 2.355 times 1.2 over, whoops, the square root of 132, n, not degrees of freedom. Or I could do 2.355 times 1.2, right? Just multiply the numerators of the fractions and then divide by the square root of 132, right? Whatever. Now remember, this margin of error is not a percentage, right? So you initially look at that, you're like 24%, that's crazy, right? That would be an insanely large margin of error. Like it would make the interval useless. But these are not percentages, right? These are numbers of credit cards. So we're estimating the true average number of credit cards within for undergrads, within 0.25-ish cards, right? So these margin of error is in numbers of cards. So this margin of error is 0.246. That's it. But there's another way we could do it. So our other option here, another way we might approach this, right? That takes away the whole element of finding the T star. I could hopefully like pause the video, right? Think about what's another way you could do this. There are other ways we have found margins of error. Like sometimes I just gave you the interval and asked for the margin of error. So what I could do here is I could go stat tests and I could actually create my T interval, which is number 8. I'll put in the summary stats. So our sample mean was 2. Where'd it go? I wrote it down. 2.6. Our standard deviation 1.2 and 132, 98% confidence. And so we get this confidence interval of 2.354, 2.846. Now remember, if we kind of visually represent this, we're starting with some X bar, 2.6. We add some margin of error to get this upper value, 2.846 in the confidence interval. And we subtract some margin of error, the same size, to get this lower value. All right, so that's kind of a number line visual representation of a confidence interval. So if I want just this margin of error, I could subtract these two numbers. I could subtract these two numbers, or remember, I could take the width of the entire interval and divide by 2, right? Because we don't want the width of the whole interval. We only want half of that. And if I, in fact, do that, 2.846 minus 2.354 divided by 2, right, I get the same answer. So another way, you do whatever works for you. All right. Now, one more problem, we'll call it a day today. That's finding margin of error, no big deal there. Hopefully felt like a lot of review with just a couple tweaks to the mechanics, because that's what it was. So next one, that's the same problem. So let's say we want to use 99% confidence to estimate the mean amount of time it takes to download some new software update. We want to estimate the mean download time, right? So once you see this, you're thinking T stuff to within 4 seconds. So this 4 seconds here, that's our margin of error. The within is kind of a keyword that gives that away to me. And it tells us the standard deviation of download times is about 8 seconds. So we need to find the necessary number of downloads we need to sample, right? So this, we got to find N to get this margin of error. So we're going to start out with the same formula. So let's go back to the whiteboard here. So margin of error, we know we want that to be 4 seconds. We know margin of error equals critical value, right? Same thing we just saw, times our standard error formula which we know is standard deviation over the square root of n. So we have, sorry that I just did all that without letting anyone see it. That was pretty dumb. So we have we've got our standard deviation. We're trying to find n. We've got our margin of error. Now, here's where it gets a little weird. Hopefully, we realize that in order for us to find the critical value for a t-distribution, we would need the degrees of freedom. I just scratch my head. But to get the degrees of freedom, we would need the sample size. So it's impossible to get t star. Right? There is no way that we can get t star because you need n to calculate degrees of freedom to get t star. Impossible. So instead, we're going to use our next best option. Really, our only other choice is we're going to use z star. So we're going to use 2.326 here because we're talking, wait a second, was it 98 or 99? It was 99. I apologize. We're going to use 2.576 here. And again, we're going to use z star, and that's because can't find t star without n. So we need to solve this equation. Now this should be, I think, much easier to solve than when we were trying to find sample size with proportions. What I would do, personally, multiply these two numbers. If we do that, 2.576 times 8, 20.608, right? And when I say I would do that, this is just based on my teaching experience. This is like, to me, this is the easiest way we could go about solving this, right? So I could have written this over 1, and to multiply fractions, we just multiply the tops and the bottoms. So now I have 20.608 over the square root of n. Similarly, I could put this 4 over a 1, and from here I would, right, unless, if you look at this blue equation and it's easy for you to solve, then whatever, do whatever you got to do, get the right answer. But if you hesitate at all, this seems to work. From here I could cross multiply, so 20.608 equals 4 times the square root of n. And then I think as we move forward, this is probably, pretty straightforward for us. Divide by 4 on both sides. So when I do 20.608 divided by 4, I get that. 5.152 equals the square root of n. And then, of course, we're going to square both sides. And remember, we're always going to round n up. Now, I know in this case, right, you're rounding n up just because 26.54, right, like that's how you round it. But even if that's at 26.1, we're going to round up because remember, when we find that n, that represents the minimum number we need to achieve that margin of error. So if we ever round down, we're going below the minimum sample size we would need. That's it. That's how you find sample size, and we'll see some more of those. In theory, I could then use this sample size, look up the degrees of 26 degrees of freedom, n minus 1, and then I could go back and redo the whole problem with that new t star now. But you don't really have to do that for the sake of the exam. But that is something I could do in real life to get a better estimate of the sample size that I would need, but not something you got to do on the assignments and on the AP exam. All right, so that's it. Have a wonderful day. I'll see you guys tomorrow. Kind of.